just give you some little bit idea about the GeoModeller. It allow us to build a complex geological modeling using implicit modeling algorithm. Intrepid Geophysics has two main software product named GeoModeller 2023 and Intrepid 3D. GeoModeller is basically designed for complex geological modeling, utilizing your geological and geophysical plus drill hole informations into it. It also provide a suitable mesh import program to export finite element meshes that can be directly go to the free flow and mud flow type of environment to do water modeling statistical analysis. GeoModeller also support the stochastic joint inversion program with the help of gravity magnetic dataset. It allow us to improve your model based on gravity magnetic information. GeoModeller also supports Worm E 3D feature 3D feature extraction program. This is basically a geophysical interpretations where gravity magnetic data can be used to extract the response of the faults in the form of lineaments. The lineaments will be stored as a deep and the contact and the deep information that can be directly used in GeoModeller to make a fault surfaces. GeoModeller also supports the automation and scripting where we can create a task file for whole modeling program, and it can share the task file to anyone to execute the same program in another system, another software, another GeoModeller user. This is quite quick and shareable. Also, it can be keep it as a record purpose, so that any future if anyone who is not aware with the GeoModeller program can use the script to see the model result. GeoModeller also has a advanced capability named Moksha program, which is nothing but a 2.5D AEM full inversion. It's basically electromagnetic inversion program. It's currently it's under the services, but we're going to add this feature in the upcoming GeoModeller upgrade. The Intrepid 3D on the other side allow us to do quality control, processing, filtering, and interpretation on the potential field dataset. Potential field dataset means the ground, airborne, marine, gravity, magnetic, and tensor data. Yes, Intrepid also support tensor data pretty well. Almost all tools of Intrepid handle the tensor. It has the capability to do it. Intrepid offers 90 plus tools, and all tools comes with an online tutorial and a documentation where there is ready references and all the workflows are mentioned over there, so that you can simply go and see how these tools are work actually. The automated interpretation for extracting the 3D subsurface feature. This is a quite useful program for the Intrepid. Almost all interpretation tools on Intrepid are support the automation process. We can simply hit the scripts and we'll get the result in a very less amount of time. Just to check if this is visible or not. Is it? Sharing the screen again, just to ensure that you're able to see the complete presentation. Okay, so we were here, we have completed the slide. Then let's move to this slide where we're able to see the Brookman syncline geological model. This slide I have included to just to show you the how complex model we can achieve using GeoModeler. And this is just one of the example. We can make highly complex geological model, no matter uh, how complex that is. It is easy to handle with the GeoModel. So here, the information that we have is the surface map, which you can see in the left side of the screen, where you see the fault information going along this line. There's some minor faults are available. So this information we can simply extract using the digitization and convert it into the 3D model. Drill hole management system is actually available in GeoModeler, where we can import the drill hole data along the lithology, so that GeoModeler can understand the layer information directly from the well and do the interpolation accordingly. You can see from this slide, cross-sectional slide, all the intersection point of the well are automatically interpolated by the GeoModeler. We don't have to digitize it everywhere, just provide some limited data into it, and it will do the interpolation by itself. Also, we can import the numerical data such as rock properties, assay along the along the wells. This way helps us to do further analysis of the rock properties and um, do some reserve estimation kind of work. It's quite useful in terms of creating a density box sets and any other property box sets in terms of doing some further analysis, volumetric analysis of the assay data. Multi-edge detection. This is a worm-E operation. This particular tool is available in Intrepid as well as GeoModeler, and this helps us to delineate the edges of the lineaments or any faulting locations with the help of gravity magnetic data set. So it's automatically detect the edge based on the gradient change in the gradient on the gravity magnetic data set, and provide us the contacts and the strike and deep information of this surface, so that we can simply convert this and convert a regular fault surface in GeoModeler. Unstructured meshing, a GeoModeler is completely interoperable with flow type of environment, and it's allow us to export finite element mesh from already prepared conceptual model in GeoModeler. This helps us to further optimize the statistical calculation in the water, like thermal, water conductivity and other statistics very accurately. So the finite element mesh exported by GeoModeler is quite accurate, and it's completely unstructured watertight manifold mesh, and it can resolve your resolution by improve this accuracy is a lot of is quite meaningful. Let me just give you some brief introduction about the core design specification of the GeoModeler. GeoModeler can build complex 3D model, which includes the fault, folds, overturned strata, intrusions, dikes, and any other information that we want to build. It helps us to incorporate digital terrain model into the model. So everything is we observe the model from the topography. It has the interpolator that that help us to create a regular surface. We deal with this statement in later slides. Rule-based modeling. This actually emphasizes we can set a rule for modeling, like the stratigraphic rule or the top and bottom rule of the sequences, so that GeoModeler can understand how we go with the model. GeoModeller can handle the sparse data very well since it's an implicit model, so we don't have to supply data everywhere. It will automatically interpolate based on the available information. It's a kind of co-creating interpolation. So it basically geology use the geostatistical operation or interpolation to make a smooth surface. It also has an advanced drill hole management system that helps you to import a drill hole and the assay data into the modeling exercise. And the one more advantage is that we can add and revise data at any point of time, or any point of modeling exercise, or whether if we get some data in later stage of the modeling, then we can simply add it into model and revise it instantly. So we don't have to go again and create a fresh model of it. We can simply recompute. We can interactively add data and revise that model and make it updated as we go with time. GeoModeller also has a flexible import-export option that allow us to export or import the data from any type of formats. So almost all software supports the GeoModeller exported mesh uh, and the grids, 3D grids. And basically, the GoKit is a more generic form of the function that can be shareable with any other software. So I think we can go with that. GoKit is available with the GeoModeller GoKit format. GeoModeller Interpolator, since GeoModeller uses the context, basically this slides is actually referring the principle of GeoModeller, how GeoModeller surfaces are built with the help of data sets. So let's assume there is a 3, 4, 5 points are available in the screen, which is actually a context, and all the contexts will be joined with a line. But how the line will what would be the position of the line, how the line will be oriented, that is defined by the orientation data. And this will be illustrated in the next slide. This is how the joining line will be oriented based upon the points as well as the orientation data. So there are two main data set that we actually provide to GeoModeller to understand how the surface will be made, what will be the shape of the surfaces. So when we do this operation in 2D, we call it kriging interpolation. The kriging is basically a type of grading interpolation method. But when we do this interpolation in 3-dimensional, then we use it as a co-kriging interpolation. I'm just going to talk about the basic of the stratigraphic pile. Any model need to build a series, like how many sequences, how many formations are there, and what are the relationship between these formation for sequences. We call it to set stratigraphic pile, and which is also a model constraint. That is a meaningful information for the GeoModeller to understand how this geology will be look like. So in this example, there are 3 series F1, series F2, series F3, F2, and F1. And you can see there's a 3 formation is available in series F1, 2 formations in F2, and one formation in F3. In the slide over here, this is this actually illustrating the relationship between the series. Like F1 series is F2 series and F3 series, how these series are actually related to each other. In this figure below, the F3 series, F1 series, F2 series, F3 series, all are overlaps. That represents that the below series, actually the F1 series will be the will be the first series which will be deposited. Then afterward, in the next series like F2 will be deposited on top of it. It's not going to cross-cut the F3 series. This is called on-lap relationship. And in other place, when we convert this F2 series to the eroded relationship, that is referring that F2 series is gonna cross-cut the older series. That means that here the F1 series. So this is how we adjust, we set the relationship between the stratigraphic piles so that GeoModeller can understand the how this surface gonna be look like. This is a real world example from the Grand Canyon. You can see here this stratigraphic pile. The older Vishnu cyst series here is intruded by the Juraster granite, which is a later phase of event. That's why we uh, uh, market the Juraster granite as an erosional surface. Then after that, there is an unconformity, which is actually a non-conformity. Non-conformity is a erosional surface, so we have to define it as a erosional surface. After that, there is a Omkar granite, Omkar group. I'm sorry, and it's just going on and sit over the non-conformity. It's not going to erode anyone. So just go and sit over the non-conformity. That's why we set the relationship like on lap. Afterward, there is a one more group called Tonto group, which has been overlain by the Onkar group, and both two group are separated by one unconformity, which is a erosional surface. That's why we have set the unconformity as a erosional surface. So this is how we actually picture the stratigraphic pile and build a relationship between the formations. This is another example from the surface map, like how we extract information from the data which is available. There's a there's a no fixed way to there's no uh, a, a, a a definite way to describe that only this way is available to read the data set. GeoModeller has the infinite possibility to import and collect the data from any information we want. So this is a one of the way we are going to describe. So this is a geological map. Most of the areas covered by the residue, like this, the and there are few areas where the erosion happened. The outcrop is visible, and there is a lot of information of the geology. If you can see, we can able to observe the lineaments. The interfaces between the formations, and we can also able to collect the deep information of this formation. And there is a fault sign along this direction and along the direction. This all information we can simply extract using GeoModeller. To do that, the first thing has to be build a geological stratigraphic pile. So based on the information available from the map, we can build a stratigraphic pile, assign the proper stratigraphic relationship, like the cover is on lap over the series. Rest of the below series are part of the one series. Formations are the part of the one series. So there's a two series like cross series case B and case B cover. So let's see how we're gonna digitize the information and able to achieve the model. The first thing we digitize this particular interfaces. Wherever the interfaces are there, we can simply digitize and assign these interfaces to the appropriate lithological formation. And we also collect the fault information from here and from fault information from here. After extracting all this information, this is how the surface will be look like. This is just intermediate interpolation stage. We haven't done this is not the complete modeling model picture, but just to give you some idea how the interpolation GeoModeller has done the interpolation. So this is the left screen is actually demonstrate showing the points that we have digitized from the map, and after calculation, after computation, mathematical computation of this model using this data, we're able to achieve this interpolation, interpolable surfaces. This actually representing the iso lines, which has the equal values over each and every lines, each on one single line actually. And GeoModeller able to calculate the orientation of the planes based on these lines. This doesn't have any geological meaning, just able to see the interpolation of the surfaces. So after rendering to the 3D geology, we're able to see this result over here. It is complete 3D picture of based on the surface map data. Uh, so GeoModeller also has a complete set of tutorials available online. You visit the website Intrepid Geophysics and go to the documentation session to documentation option to get this all information. There are plenty of case studies are available that you can use there, and the concepts behind the modeling exercises, API interfaces, and the tutorials and helps on each and every cases are available over there that you can use for your reference and during your exercise stage for your learning purpose. So, okay, this is what the introduction is, and now I'm going to start the demonstration. Yes, so uh, let me just give you some brief introduction of the GeoModeller interface. This is the project. This is basically a GeoModeller basic interface that we are looking at right now. There are various options for project creation, saving the project, and the properties of the project. And we also have the geology model where we can create geological formations, manage the formations, create the dikes, stratigraphic pile and manage set. That is actually for building a stratigraphic piles and assigning the relationship between the formations, the visualization of the stratigraphic pile, creating faults, and link the faults with the series that what series the link was affected and the fault was affected, and there is another option called link fault with the fault. That means sometime there's a mother faults which stop the daughter faults. This kind of relationship we can simply adjust from here. Then there is a model computation. This actually option used to compute the modeling algorithm, mathematical calculation based upon our input data set. Then the geophysics, we can define the physical property of each and every formation, either it is density, susceptibility, resistivity, for doing forward and inverse calculations. Also, we have a warming tools to extract the lineaments from the gravity magnetic grid. We can also examine the geophysical grid from this option. Then the interpolator. There's a option available to uh, analyze the data, prepare the data, and do some statistical analysis using this option. And we also have the variogram analysis that is quite an important one for doing the uh, geostatistical analysis and do the kriging interpolation based on variogram analysis. Then one more option for kriging is the domain kriging. This is a highly advanced kriging method where we also use directional uncertainty to create a 3D grid, and the Gaussian solution. This also helps us to emphasize the transformation, and these are some kind of statistical uh, uh, information that we can get from here. And then the import and export option, where we can simply import the GIS data, which could be a save file or any database from like GDB or DIR, ArcShape. And then 2D geology to the section, we can simply import is a 2D layer information in CSV format or BRGM DATA format. And also we can import the orientation data set, which is available in CSV file. Then if we have some XYZ information, like in 3D form of interfaces, that also can be imported. This probably we can get from seismic interpretation or any geophysical interpretation of the basement or any other surfaces, which is provided as a point location. Then orientation, then apparentive. There's a lot of option over there. Then exporting, the model export, we can simply export our model from this option. There's a various viewer adjustment and control section over here, so that you can simply go and select the uh, the quick tools from this option, and the window to set the prospect view and research. This is a quite advanced menu. I suggest please do not uh, make any changes. Go and explore these options if it is helpful for you. And then the help, the manual and tutorial. I would like to just give you some information from here. So this is a tutorial that you can directly access from that link, where you see the introduction to the GeoModeller and GeoModeller interfaces, API, GeoModeller parameter and concepts. So any information, if you like to know, just search here and it will give you the result, like forward. Okay, so it's giving me the forward modeling and inversion introduction, and very similar, and the results similar to this, similar to the what I have searched for. So I'm just going to start with a fresh modeling exercise. Since I already have created one, so I'm just going to set the project coordinates. And the location, GTK training. Okay, so this here, test. I'm just going to define a project name test. Select this folder. This is for training. So I have actually set the directory location of this train location of this project, and I've set the project name by the name training, and the project location that is actually displaying over here. We can set the author name. If you want to set your name or any who is actually creating this model, you can set over here. Date and time will be recorded based upon the information or your current date and time. And the most importantly, we need to set the projection coordinates information. Projection coordinate information for this model would be GDA, sorry, MGA. GDA 94, MGA 55. I don't know about the project locations. I'm just going to go and check the locations from the tutorial. Here it is. It's saying the Australian grid MGA 55 and GDA 94. This is fine. This is accurate. Then 416. Okay. 416000. Let's input this by selecting it manually. It's not working like that. 433. It's the right list. So now I have set the location, uh, location of my boundary box, coordinate of my boundary box, and I'm just setting the Z minimum to the 2 kilometer deep and Z maximum up to 1,000 meter, 1 kilometer up to the mean sea level. So I think we are good up to here. I'm just going to hit OK. It asking to load the DTM grid. In case you don't have the DTM data, you can simply go for this option where you can define the horizontal plane at any particular height. So in this case, we do have the DTM data set, so we're gonna use this option. And here, to the surface topography, I'm just going to locate the data set. This is the grid data for the topography. I'm just going to import here, and I'm just going to click OK. So it's actually working to create a project for us. So this is the main field syncline project that we have created. If you go to the project and properties, you're able to see the coordinate locations that we have entered and the projection, this projection that we have selected. Just to review in case you have done any mistake. So we have 3 sections in this interface. The left one is for the project explorer, where we can see the components where we import the data. Whatever data we import and digitize will go and set over here, and we can simply adjust and review and remove and manipulate the data from this section. And the middle one is the 2D viewer editor section, where we can basically work upon, like we can edit we can remove add data in this section. And the 3D viewer, the right one, is just to visualize, just to give us a 3D visual, 3D picture of the model that we prepare in any stage of our modeling exercise, just to see whether the model requires much improvement or need any further data. So we can simply review it here and in and revise the model based upon the observation what we get. In the grid and meshes section, there's a DTM grid. DTM grid that we can that we have loaded during the project creation. So this is basically a grid file. Right click over it, go to the field visualization manager, and here we can project this grid on either section or in 2D and 3D section, 3D viewer. So in this case, I'm going to project this grid on 3D viewer. I'm just going to select this and click OK. So this is the 3D view, 3D topography of this model. So topography is actually important because uh, the interpolation has to be in limit up to the topography. We don't want to model above the topography. We just wanted to model below the topography. That's why it's a kind of stopping limit of our model. So this is what the topography is look like for the Mansfield. So now the first thing we'd like to do is we have to just import the image of the surface topography onto the topography. Yeah, sorry. The geological map of this Mansfield syncline uh, to import it on the topography. So this is a geotiff map. So it's already uh, has detected the coordinate references and the proper coordinate system. Since our project is already geolocated, so it understands where this point has to be located on the project. So based on that, it has adjusted automatically. You just have to click OK. In case you're using the JPG or any unregistered map, in that case you have to georeference it based on the coordinate of the point. You have to manually enter those points into these locations for 1 2 3 for 1 2 and 3 points. At least 3 points is it's necessary to make a map geo-registered into a section. So we're just gonna continue with OK. It's saying your georeferencing has been done, and here's the image that we have imported. I'm just going to hide this image from the surface topography section, hide it, and now I'm just going to show it in 3D viewer. So this is how your image is look like in 3D viewer, which is actually a topography outcrop map. So if you look it closely in the map, there's a number of information available, like layer sections, the interfaces of the formations, and also the deep information of the lithology of the formations. Yeah, let's say. So these information we can simply extract or digitize to create a 3D model out of this map. But let's just first thing import the drill hole data. To import the drill hole data, we go here in the import option, and the drill hole option is here. We can simply go through file color survey and geological file that which is already available in your practice data set. So this wizard is actually helpful to import the drill hole information. It required three separate files like color, survey, and geology. So to import this file one by one, you have to go to the this option here, GTK training dataset folder. There is a synthetic drill hole folder is available where color, geological, and survey CSV file is present. So you can select the color files and import it one by one. This is for survey and this is for geology. Click next. Yes, so now you can simply review the information that is available in CSV and what information GeoModeller is actually reading from this CSV file. You can review from here step by step and and, uh, and move forward. So in this color information, these information are available in the Excel sheet CSV file, and this is the information that GeoModeller is looking for in terms of color. So we need to carefully check each and every column that is properly aligned with the required information or not. So X is actually aligned with easting, Y is northing, and Z is the color height. The Z is actually the color height, which is required by GeoModeller. And this is the survey file, which actually uh, contain information of the inclination and deep of the azimuth and the inclination of the well. Sometime wells is not well is not always vertical. In some cases it may be tilted in some direction. So based on the inclination of the well, this information could be provided to make the well to make the well visible tilted in the 3D GeoModeller interface. So this is the information contains the CSV file, and this is the information that GeoModeller is looking for in terms of survey data. So we need to carefully match this again. Hole ID is with hole ID, deep is inclination, bearing is basically a synonym of same thing. It's basically same terminology. And the survey depth has to go to the survey depth. Then click next. So this is basically a geological file where the information is available for the geology. Like it's kind of interval data where from what interval to what interval is what type of geology is available, something like that. So we need to since this information in CSV is already in a single code, so it's not actually detecting properly. So we need to separate it using these delineation methods. So now it's properly aligned. This is okay. So in terms of geological data, GeoModeller required the information like hole ID from depth to depth and geological code. And this is automatically detected by the GeoModeller, but just have to recheck again that all information are aligned with the required information. So once we click OK, there is an option how we gonna import this geological unit. There are several options to do that. In this case, we're gonna create formation name in GeoModeller because we haven't created any geological stratigraphic pile yet. So with the help of import, we're gonna create this formation name so that we can set the stratigraphic pile using this information. Click next. It's showing that your drill hole is valid and fulfilling the criteria for importing this in GeoModeller. You just hit click OK. Now you can go to the drill hole, right click over it and click on show. You're able to see the drill holes are actually displaying on the 3D viewer. let's set the radius to 100 to make it uh, wider. Now uh, it's look good. Let's project this geological sorry, the drill holes to the surface topography. Since this geological model, top of the wells should be intersected on the topography. So we're gonna project data onto the section in 2D viewer option. We wanted to project our drill hole to the surface topography with the projection distance around 20, since it already intersected the topography, so we didn't have to give the projection distance too high. So here we're able to see the old wells information from the vertical view. You see the drill hole information. This is DH1, this is DH2, 3, 4, 5. If you want to look at the cross-sectional view of the bit, you have to create a cross-section by taking pencil and digitizing a line along the well. Once you created a line, you just go here, the shortcut key for creating section from a trace, and create a section by some name. You see, we have created a new section called section 1. If you click over here and project again the wells along the section 1, in this time we have to keep the projection distance higher, because well, maybe have some deviation from the line. So this is actually the wells, location of the wells along the sections. You can see it from here, and also can be seen from the 3D viewer. Now come back to the plane surface. We already have the geological map that we can see. We can extract information from this. Then with the help of GeoModeller for drill holes, we can simply revise that model and make a constraint up to the depth. So the first thing, okay, we have to create the stratigraphic pile first. So go to the geology and the stratigraphic pile manage. Here we already have created the formation names. Just have to assign the name, the formation to some particular series name, so that we can set the relationship. To do this, we have to go to the here new series, and we in this section we able to see the name of the formation that we have created. So in this series, in this exercise, we're gonna build two series, one for Mansfield series and one for basement series. The Mansfield series contain three formations, like upper Mansfield, middle Mansfield, lower Mansfield. This is based upon the already understand stratigraphy. If you are modeling a geological model, you must have prior understanding of the geology based upon the literature or any other surface area maps, or so that you can set the law accordingly. So once we set the Mansfield series, we have to hit commit, so that it will finish the setting criteria. Then the basement series also have to commit. It's okay, it's done. So now we able to see two series, sorry, two series, and both are having the overlap relationship with each other, we can we can we can simply set these two series based upon the chronological sequence. But right now they are in order, so we're not going to disturb anything. Just one thing, we it would be better we can make this reference to the bottom. That means whatever we digitize will represent the bottom of the formation, not the top. Whatever data we incorporate or import will treat it as a bottom of the particular formation. So once we happy with the stratigraphic file, we can simply close it. Now we can see these informations are here and the basement informations. Then the next thing is to import the geological layer. There's many way we can do this. Like we can simply digitize the upper Mansfield bottom layer by taking a pencil. I'm just taking just a random hit, or I already have the digitized uh, coordinates saved as a CSV. I can import that into this section. For that, you can simply go here, import, and hit the contact CSV option. Then go to the upper Mansfield contact and deep information, data from other fields, and we go here, contact upper Mansfield 2D CSV, and click open. Okay, then click next. So this is actually coordinates of the points of the upper Mansfield on the surface topography. Just click next. Here we need to careful about the geological formation has to be set to the geology, and geology is the upper Mansfield. That means this information is going to sync with upper Mansfield data. You see here, we're gonna import this data set in to upper Mansfield geology. Once we hit OK, it's actually has been loaded, but it's not visible completely. Just let me just increase the length, sorry, the width of this line. Now it's visible. Yeah, this is visible, but because of the same color, it's actually transparent. I can change the color as well. Let's just change it to green. Okay, it's also coinciding. I think yellow would be better. This look better. So this is how we imported the geologic the upper Mansfield's bottom layer, bottom interface. So as we already know that we need two type of information to make a interpolated surface. That means one is a contact and one is a deep. That means the orientation data. This is how the surface is going to be positioned itself to during the interpolation. So this information we can use to 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 adjust our shape of the surfaces. We already have digitized these information in the form of CSV. We're gonna simply import this. This is the orientation option to import. Deep information of the upper Mansfield. I'm going to import this file. Click next. Go to next. And we have to set this formation to the geology. Rest of the formation is completely is okay. Click next. Then I'm importing the upper Mansfield. It's saying that all 35 information has been imported. You see, all orientation is now marked by the valid data readable to GeoModeller. So now we have at least fulfilled the criteria of one model. Just gonna go ahead and compute this model. Okay. Okay. So for model computation, you just hit here, compute. Either you can go here and press the same option. So this actually representing the series that we want to interpolate. This Mansfield series contains three formations. One formation we have digitized and two other formations we haven't digitized. But since it's a part of one single series, the context point of rest of the formation that we haven't digitized will be taken from the drill hole data. In case we don't select the drill hole data, the interpolation series is actually not valid that time. It's not allow you to interpolate all three layers. In that case, you have to digitize rest of the two formations like middle mains and lower mains in that case. So that is another thing we can do. But in this case, we already have the drill holes. So why don't we use drill holes to make this surface, make this model? So we select all and select all the data which is available, either series, faults. There's no faults right now, but once we incorporate some fault information, the fault body will be displayed here. The section, whatever section we digitize, every section will be displayed here, and the drill hole section. So we select all information for the model computation, click OK, and now we're gonna plot this the computed model. The model computation is so quick, you cannot able to recognize it how quick it is. So it's done automatically. It's done. It's a matter of seconds. So once the computation is done, we can plot the model into the section. I'm just going to plot this model on the topographic section here over here. We have plotted the model, but since it is not visible, we simply has to hide this geological map. So now we're able to see the structure of the basin, three layers, four-layer structure of this model on the topography. Also, if we go to the section, we can project. Once your model is built, you can project your model in any section you want. So I'm just wanted to project our interfaces, line interfaces along this section 1. For that, I'm going to just plot the model setting again, and this time I'm just removing the fill so that only lines can be seen, the interfaces line, and it's actually coinciding the interfaces that is available in drill holes without even digitizing it. So at this stage, what information we have provided, we only have given first layer information, the first upper Mansfield information of deep and context, and the well data. So up to this stage, we able to achieve a model. Let's visualize this model in 3D view. For this, you just have to click here, visualize 3D formation and fault, increase the render quality to the high or maybe medium at this time. Your render quality depends upon the cells of number of cells of this model. High number of cells, you will get a high resolution of your model, but it will take time if you are increasing the number of cells for rendering, to process the rendering program. If I click OK, the marching tube is in process, and we're going to see the model in 3D view very soon. Yes, so this is a 3D picture of this model. Up to this stage, we have only incorporated the first layer information. Let's see where we are. So the first layer information has been introduced. The second layer and third layer, that middleman's field and the lowerman's fields are not properly aligned as per the geological map. So we have to use this information to update this model. To do it, we can simply import already saved contact information for Mansfield, middle Mansfield data. I'm going to import the contact quickly and the orientation, geology, next. I'm just going to import this. Okay. So this is just let me just remove the previous model so that I can able to see the actual data. So this is the middle Mansfield line, the geological interface. I'm just going to increase the line width to 4. Now it's look more it's look visible and actually coinciding the interfaces properly. Then I'll just going to import the orientation data of the Mansfield. It's a middle Mansfield orientation. Just go quickly on the set the appropriate information right away. Click OK. So you see the orientation of the middle Mansfield now has been incorporated properly here, here. Now it's time to import the lower Mansfield contact surface. Contacts. Geology. And this is the lower Mansfields. You able to see the line width is so thin, that's why it's not visible. I'm just going to increase the line width now. Up to this stage we have incorporated one more thing. We just have to add the orientation data for the lower Mansfield. We haven't done this yet. Geology, click next, finish. Okay, so now we have extracted all the information from layers. You see it's actually marking the appropriate line of the interface. Now we can simply go and compute this information. Compute, select all, including drill hole, and now we just have to hide this and just go here and plot the model setting with all the information. So now model look updated using the latest information that we have provided. If you look the final model in 3D view, just take some time since the model was updated with some more data. You see this this is the model surface, the 3D volume of this Mansfield model. We can visualize by the multiple options here, where we can clip this from multiple directions, from XY directions, to see the geometry, how the geometry look like from above, then from side. So these are the options that are available. Also, you go here to the geological section, and we can simply hide layers one by one to see what are the shapes of each and every individual layer, and how well it has been aligned with the well locations. So this looks good. Up to this stage, we're able to achieve the appropriate model. Then what else we can do is just we can take sections and along any direction from here to here, or just take any sections. I've created one new section, cross section, and section number 2, and I'm just going to visualize this ready model into this section with all the model setting. So this is a section that we have simply projected the current model. Uh, so a GeoModeller allows us to create as many sections you want to extract this information. And also, if you need to import this model as a map or as a located image, you can simply click over it and go to the image manager. Sorry, this is not the right option. Go to the save image, and you can simply put some name of the image. New, okay, PDF or TIFF. I just select the TIFF by this name. Click OK. Go to the image, and here's the new TIFF. Sorry, it was saving actually. So this is the surface topography in the TIFF image. Sorry, the cross-sectional image of the TIFF image. Also, we can make some presentation to look it more presentable. Then extract. Then the save image as a PDF. Okay. New, sorry, section PDF. Save section PDF. So this is how we export images of layers for the presentation purpose. Apart from that, we can visualize this section in 3D viewer for fence diagram kind of operation. Right click over it, so model geology polygon in 3D viewer. Here you see it's getting a much clear idea of the orientation of the geology and how geometry is actually varying from what depth to what depth. It's quite meaningful. So after creating this model, we can simply export this model as a box set, or export this 2D model as a box set. Just go here and select model. Sorry. Click OK. May take some time, but output. So this is your worksheet, which is a BOX mesh file that can be supported by any other software. And this is XYZ format. This is a basically XY, this contained XYZ information. But this is a worksheet file. This is supported by any other software. Apart from that, you can simply create a 2D, 3D grid from this model, where you can use 3D model and choose the appropriate gridding spacing. I'm just going to create a grid from 20. Okay, sorry. Okay, 2D model grid. This is what a discretized grid is look like. The cells, I haven't used the smaller cell size, otherwise it will take much more time to create this grid. It just to give you some demonstration on how we can create a discretized grid using 3D model. And this grid is can be exported in any other formats like CSV, UBC, Voxset, GoCAD as grid for your further analysis and to be used in any other software. So this is it. I think I have covered this exercise during the tutorial, and this is just a basic understanding of the GeoModeler. By building a simple model, this exercise will help you to touch maximum option available in GeoModeler, which could be helpful for to understand the workflow of the working environment of this GeoModeler service software. In the later exercises, we will deal with the faults and numerical data interpolation in 3 dimension. It will quite um, uh, it will be good if you can do the exercises and keep this uh, exercise ready for further discussion. That would be more better and fruitful for you. So we'll discuss it later at some other time. Maybe SEDA, when SEDA is help us to decide some of the date where we can simply involve and have this further discussion of how we go with other sessions. We'll discuss it then. So thank you so much. I hope you enjoyed this session, and I'll be more happy if you come back to me on my email and write to me for any other doubts or any other information you need regarding the GeoModeler. I would be happy to provide you more information on that. Thank you so much. Have a nice day. Okay, great.